Fields. What is a field? Fields are fundamental algebraic structures on which the operations addition and multiplication are defined. These structures are widely used in algebra, number theory, and many other areas of mathematics. Let's have a look at the formal definition. A field is a set F with two operations called addition and multiplication, which satisfy the following so-called field axioms: A, M, and D. Here A stands for axioms for addition, M stands for axioms for multiplication, and the distributive law, which combines the operations addition and multiplication. Axioms for addition. A1. If X is in F and Y is in F, then their sum, denoted by X plus Y, is in F. A2. Addition is commutative. Means X plus Y is exactly same as Y plus X for all X and Y in F. A3. Addition is associative. X plus Y plus Z equals X plus Y plus Z for all X, Y, and Z in F. A4. There exists an element denoted by this symbol 0 in the field such that X plus 0 equals X for all X in F. A5. If X is in F, then there exists an element denoted by the negative X in F such that X plus negative X equals 0. Here, the 0 is called the additive identity element, and this negative X is called the additive inverse of X. By commutativity of addition, A2, the last statement can also be written as negative X plus X is 0, the additive identity element. Axioms for multiplication. M1. If X is in F and Y is in F, then their product XY also is in F. M2. Multiplication is commutative. Means XY equals YX for all X and Y in F. M3. Multiplication is associative. Means X times the product YZ equals XY times Z for all X, Y, and Z in F. M4. There exists an element denoted by this symbol 1 in F with the property that 1 is not same as the additive identity element, such that 1x equals x for all x in F. This one is called the multiplicative identity. In particular, if X is itself the multiplicative identity, then this relation gives 1 times 1 equals 1. Hence 1 squared equals 1. We should read this the product of the identity element with itself gives the identity element back. The next axiom for multiplication. If x is in F and x is not the identity element, the additive identity element, then there exists an element denoted by this symbol. We may read x inverse in F such that x times x inverse equals 1. This is called the multiplicative inverse. Of x. Note, x inverse is just a symbol whose definition is clear in this statement. By the commutativity for multiplication, axiom M2, we can also write this statement as x inverse times x equals 1. The last axiom, the distributive law. X times y plus z equals xy plus xz. And this holds for all x, y, and z in F. This axiom combines the operations addition and multiplication in a single statement. Example. The field axioms clearly hold for a set of rational numbers. Thus, Q is a field. We can also say the field of rational numbers. The set of integers Z is not a field with the operations addition and multiplication. For instance, the axiom M5 doesn't hold. For example, there is a number 2 in the set of integers, but there doesn't exist any element in Z such that 2 times the number gives us 1. Proposition. Let F is a field and X, Y, Z are in F. Then the axioms for addition imply the following statements. A. If x plus y equals x plus z, then y must be equals to z. By commutativity, we can also read this as if y plus x equals z plus x, this would imply y must be equals to z. B says if x plus y equals x, then y must be equals to 0, the additive identity element. C, if x plus y equals 0, the additive identity element, then y must be equal to the additive inverse of x. Mathematically, y must be equal to negative x. D says the additive inverse of the additive inverse of the element x is exactly the x itself. So the negative of negative x is x. These properties are true for any field, not necessarily for the field of rational numbers. The statement A is called the cancellation law for addition. For example, it says if x plus y equals x plus z, then x must be equals to z. So we can simply cancel x from both sides. So this statement A justifies the cancellation for addition. We will prove this property shortly. The statement B says if x plus any other element is x, then y must be equal to the additive identity element. So this guarantees that the additive identity element 0 is a unique element in a field. Similarly, the C does the same thing for the additive inverse. For every element X, there exists only one additive inverse element in the field. Let's have a look at the proof of the statement A, namely the cancellation law for addition. We want to show that if x plus y equals x plus z, then y must be equals to z. Simply, we can cancel the x's from both sides. Let's prove it. We begin with the statement that y equals 0 plus y. Since y is in F, then we can apply the axiom A4 to y. Then the 0 can be written as negative x plus x by the axiom A5. Then we apply the associative law for addition, which is the axiom A3. And by hypothesis, x plus y is same as x plus z. Then we can apply the associative law for addition, which is A3, and a repeated application of A5, namely negative x plus x is 0. We get the step, and then we can apply the definition of the additive identity element of 0, A4. 0 plus z is z. So we proved that y must be equals to z. This is the end of the proof of A. Let's try to prove the statement B. It says if x plus y equals x, then y must be equals to 0. So we begin with the hypothesis that x plus y equals x. Let's keep the left hand side as it is and replace the right hand side by x plus 0, which is the application of the axiom A4. And now, by applying the cancellation law for addition, we just proved we can cancel x from both sides, and this leaves us with the statement y equals 0. This is the end of the proof of B. Now we prove the statement C. It says that if x plus y equals 0, then this would imply that y must be negative x. We begin with the statement that y is equal to 0 plus y by the axiom A4. Then again, we replace the 0 by negative x plus x by the axiom A5. Then by the application of associative law for addition, A3, we obtain this statement. And now we apply the hypothesis that x plus y is 0. And then we apply the axiom A5 that for any element x or negative x in the field element plus 0 is the element itself. So this shows that y must be equals to negative x. This is the end of the proof of C. Let's try to prove statement D. It says the additive inverse of the additive inverse of an element x is just the element x itself. We begin with the statement that negative of some field element plus the field element is the 0. But this 0 can also be written as a field element x plus its additive inverse. And now, by the cancellation law we proved in statement A, we obtain that negative x equals x. This completes the proof of the statement D. Please pause the video, go back a few moments earlier, and read the proofs again. Proposition. Let F is a field and x, y, z are in F. Then the axioms for multiplication imply the following statements. A. If x is not equal to 0, means it's not equal to the additive identity element, then the equation xy equals xz imply y equals z. By commutativity, we can also read as yx equals zx implies y equals z. So this statement, A, is the cancellation law for multiplication. So if we have xy equals xz, and if x is not equal to 0, then we can simply cancel to obtain the equation y equals z. We will prove it, just like we proved the cancellation law for the operation addition. Similarly, the statement B says if x is not equal to 0 and xy equals x, then y must be equal to the multiplicative identity element 1. C. If x is not equal to 0, then the product xy equals 1 imply that y must be equal to the multiplicative inverse of x. So this statement guarantees that there exists a unique multiplicative inverse to every element in the field F. D says if x is not equal to 0, then the multiplicative inverse of the multiplicative inverse of an element x is just the element x. Let's have a look at the proof of the statement A. We begin with the statement that y can be written as 1y by the axiom M4. Then 1 can be replaced by x inverse x. Since x is not equals to 0, we have the multiplicative inverse of x. And then by the associative law for multiplication, we can write the previous statement here as x inverse times xy. Now by the hypothesis, xy can be replaced by xz. And then again, we apply the associative law for multiplication. And the first term here can be replaced by 1. So by the definition of 1, the multiplicative identity element, 1 times z is z. So we arrived at the conclusion that y equals z. This concludes the proof of the statement A. Similarly, you can try to prove the rest.